Crosstalk or near field coupling, module 4.3. In this module, we consider crosstalk combination, that is a combination of capacitive coupling, inductive coupling and common impedance coupling. So what is shown here is the equivalent circuit or the model for capacitive and inductive coupling combined into one. You can approach it like that. Ignore this part IC, and then what you get is the situation for the model for inductive coupling. And if you ignore this source Vi, then you get the situation representative for capacitive coupling. The source Vi is given by the mutual inductance between source circuit and the victim circuit, and di by dt, di2 by dt, where this current I2 is in the source circuit, not the current in this circuit but in the source circuit. So this source is independent of the circuit parameters over here. This is in frequency domain, minus j omega mi2. Similarly, for the capacitive coupling part, the source IC is given by C12 dV12 by dt, where C12 is the coupling capacitance between the victim circuit and the source circuit, and dV12 is the voltage difference between source and victim circuit. Again, this current is independent of the victim circuit over here. So in frequency domain, IC equal to j omega C12 V2. Now we have the series inductance L, that is applicable for the victim circuit, and you have the capacitance to the reference CR. So this in some cases can be neglected, but not always. So as a matter of practice, always include the series inductance and parallel capacitance to the reference when you draw the model. Then check to see if one can conveniently neglect them or not. So we can neglect CR if 1 by omega CR, that is, if this impedance, capacitive impedance, is far greater than the impedance at the end. So in that case, we can neglect this. So this has to be checked always and made sure before neglecting it. Say for example, if the far end resistors or impedances were higher, say of the order of 1 mega ohms or something like that, and this capacitance and the frequency is extremely high, of the order of 100 megahertz and all, these conditions may not be true. So one has to really check that. Similarly, the series inductive impedance LS can be neglected only if this is far less than the impedance at the near end and the far end. So at very high frequencies, sometimes these conditions may not be true. So one has to really check that, these two conditions, before removing this capacitance and before removing this inductance. Now assume that we have such conditions as given above, and we neglected the capacitance and the series inductance. Then in that case, the model is reduced to two resistors at the near end and far end and two voltage sources, one representing the inductive crosstalk and the other representing the capacitive crosstalk, or magnetic field interaction and electric field interaction. Now note that we have reversed the polarity here to be consistent with this near-end current over here. So the negative sign in front of this M is absorbed into the source polarity. Now for finding the voltage across this near-end Vn and Vf, we can apply superposition theorem of the circuit analysis. So let's say Vi equal to 0, that is only the capacitive crosstalk is available. Then in that case this current In is shared, IC is shared between this and this, so it is In will be Rf by Rn plus Rf times IC, from circuit analysis, and this is for IF. So you have different currents split, but then it is in terms of voltage, then it will be multiplied by Rn, and here it will be multiplied by Rf, that we will see in the next slide. Now if IC equal to 0, that is inductive crosstalk only, so if it is not there and only the series voltage source, then this voltage is drop across this plus this. So the voltage drop across this, the total current In equal to minus IF in that case, and this Vn will be Rn In and Vf equal to R of IF. So In with inductive crosstalk is this Vi divided by Rn plus Rf, and If is minus Vi. So if you combine these two together, we get the near-end current, and this is the far-end current. So in general they are not equal. Now let us see multiplied by this terminal impedances to get voltages Vn and Vf. So we have the two sources here, Vi minus j omega Mi2 IC, then we write it down, In If, so Vn Vf. So Vn is written by this expression and Vf is written by this expression. Now the first term in this represent the inductive coupling, and the second term in both represents capacitive coupling. You can immediately see some interesting properties. Say if you look at the capacitive coupling, whether it is near end or far end, they are identical. Rn and Rf need not be the same. Even then both will be equal and they have the same polarity. Now here, if you look at the inductive part of the coupling, one is here it is positive and here it is negative. In the near end it is positive, in the far end it is negative, and they have different magnitude because in general Rn is different from Rf. They will have same magnitude but opposite polarity when Rn equal to Rf. Also you will see that in the near end the crosstalk voltage is higher compared to the far end, because here these two terms are cancelling, or they have opposite polarity, here it is same polarity. So near end crosstalk is higher. So remember that near end and far end are in relation to where the source is in the original circuit, because we drew the source in the near end, the source of in the source circuit, we have the source in the near end. So that is the near end, the other one is the far end. So inductive and capacitive coupling, what I said just above is recapped here. The capacitive coupling part is same for both near end and far end, whereas inductive part is different. So in general, Vn is not equal to Vf. So crosstalk voltages at near end and far end are different. Near end crosstalk is larger than far end crosstalk. Inductive component of the crosstalk produces opposite polarity voltages at near end and far end. Their magnitudes are also different unless the impedances are matched. The capacitive component of the crosstalk produces voltages of same polarity and magnitude at both ends, even if the impedances are not matched. Assuming that the source circuit is not influenced by the victim circuit, that is the weak coupling, then the sources I2 and V12 are independent of Rn and Rf. In that case, capacitive coupling is dominant for large victim circuit impedance. So all these things we can observe from the model. Now we also add the common impedance crosstalk to the equivalent circuit. We neglected the parallel capacitance to the ground and the series inductance. So this is the common impedance. Since the current is flowing, assumed to flow like that, so this is with positive polarity. You can see that the noise from the common impedance coupling, and this is the noise from the inductive coupling, and this is from the capacitive coupling. So if you look at, if you write the equation, so here this is positive, taken as positive polarity. So this is due this term. Sorry, this is Rf. So this is this term, because Vi is equal to minus j omega I2. So this minus is coming from that one. And this is this minus and minus j omega I2. So they cancel, so it becomes plus. This is the inductive part, and the capacitive part, they are the same. And for the common impedance part, here it is minus, because it is the current is driven like that. So in the far end part, minus Rf by Rn plus Rf ZCI2, and here it is positive. So the polarity of common impedance coupling, the voltage across, and the inductive coupling, the voltage across, they are the same. And similarly here, both are negative. So common impedance coupling somewhat behaves more like inductive coupling, except that this need not be a function of frequency, whereas this is a function of frequency. This can be a pure resistor, or it could be a function of frequency also if there is some inductive element involved in the common impedance. Now in this case also we find that near-end crosstalk Vn is always higher than crosstalk at the far end Vf, due to this negative polarity. For capacitive and inductive coupling in general, Vn is not equal to Vf in general, and polarity of Vn induced is not equal to Vf induced. They are opposite polarity. Even if Rn is not equal to Rf, Vn, the component of Vn and Vf, due to capacitive coupling alone, they will be equal. For common mode coupling, the common impedance crosstalk ensures a minimum crosstalk voltage at low frequencies, because when the frequency is extremely low or zero, you can see that these terms are disappearing, these terms are disappearing. But because of a DC resistance of the common path, there will be some common impedance coupling. So common impedance coupling always increases Vn total. However, Zc increases VF total if inductive part is dominant. So if this part is negligible, so if it is a low impedance circuit in general, so this part may be dominant, then common impedance coupling increases the far end crosstalk and also increases the near end crosstalk. But if capacitive coupling is dominant, then it increases the near end crosstalk but may decrease the far end crosstalk. So you can find some difference between near end and far end with common impedance coupling. So that ends module 3. Thank you.